Y gracias a todos los organizadores. Y voy a tomar un pequeño descanso o descanso, pequeño descanso en el medio de la charla porque no puedo hablar por 90 minutos, es mucho, necesito tomar un pequeño descanso. Pero voy a cambiar en inglés ahora, discúlpenme. So I would like to talk about optimization problems in learning, and I want to demonstrate to you that there are many, many areas of learning, not just deep learning, where optimization plays a really important role. And I just want to run through a lot of problems in learning and show you how they're formulated as optimization problems. I won't talk about how to solve them, because that's a whole other talk, or series of talks, and I'll say a little bit more about that tomorrow. But today we're just going to focus on various paradigms in learning and how they're formulated as optimization problems. So first I'll give a little bit of context about data science and optimization. Then I'll talk about these 13 application areas. I'll say a little bit about deep neural, muchas gracias, about deep neural nets. Other speakers are going to say much more about neural nets, and they are much more expert on that area than I am. And then I'll talk about some current areas of investigation that are very active at the moment that involve both optimization and learning. So there's a list of those there, and I'll get to those at the end of the talk, and then I'll give some final thoughts. Okay, so first a little bit of context here. So first of all, data science, there's many different terms that are used that sort of are vaguely synonymous. AI is a very popular term now in the press these days. Machine learning is also quite popular. Data analysis is a little more wonky. Statistical inference, a little bit more technical. They sort of mean roughly similar things. But the basic idea is that you've got collections of data and you're trying to extract some sort of meaning from them, understand the statistical properties of the data, learn some stuff about what are the important features in the data, what are some fundamental structures in the data, and then to go a step beyond that, to use that knowledge to make predictions about future data, put that knowledge into action. So I would say that's kind of, what this general area is about. It's very multidisciplinary. It's got foundations in statistics. Statistics people used to say at one point, well, we really own big data. That was 5 years ago. They like to claim the area for themselves. But of course, there are many other areas that are involved as well. There are different areas of computer science. So AI, of course, has deep roots in computer science going back many years, and so does machine learning. Database systems, on the system side of computer science, database systems, parallel systems, and also the whole area of designing architectures, they're all relevant to data science these days because they're such compute-intensive areas. And then, of course, optimization, which is the focus of this talk, provides a lot of the tools for modeling problems in data science and solving them as well. And then data science is very much bound up with applications in certain areas. So areas like signal, speech processing, vision, image processing, and robotics, areas of electrical engineering, computer science, and so on that have now become very much tied up with data science because of the great success that machine learning has had in contributing to those areas. There's a quote that I heard first from Dave Donahoe that says that 80% of data analysis is spent on the process of cleaning and preparing the data. And so the point here is that very often the collection of data that you have to work with is very dirty. It's not a nice, clean collection of feature vectors. And so a tremendous amount of work is needed to get it into a form where you can actually do the analysis. And so many of the people that work in data science in industry are involved in this process of just cleaning the data. And what I'm going to talk about today is really the last 20%. And once you've got the data in a clean form, then how can you analyze it and use formulation solution techniques to learn something from it. So I don't need to spend much time on this slide because we all know this is the age of data. Enormous amounts of data are being collected about all of us all the time. There's also in science, there are now new scientific instruments that are spinning off enormous amounts of data. In biological sciences as well, tremendous amounts of data being generated. astronomical sciences, experimental physics, and so on. Powerful computing hardware now has made it possible to do stuff with these huge data collections, as well as methodological advances, which I talk about here. There have been advances in algorithms in areas like compressed sensing, regularization, design of neural nets, and so on. But computing hardware has really driven much of this, the fact that computers have gotten so much faster, and also people have figured out how to use parallel computing and use it in these areas to run the algorithms. And then there have been tremendous successes in certain applications that have been very high profile. And you know, in areas like speech processing, the speech processing capabilities of your smartphone are really remarkable, I think. And things like Siri and Google and so on are amazing at answering questions. It really is remarkable advances. So that's driven a lot of the interest in this area. So what about the role of optimization? Well, I have this quote that I think I first said this about 4 years ago, and several of my colleagues in optimization have really picked this up, that I think optimization is being revolutionized by its interactions with machine learning and data science. There's a lot of new research in optimization that's being driven by these areas. People in these communities are now doing fundamental work in optimization. So if you go to conferences like NeurIPS and ICML and so on, you see big sections of papers that are really basic optimization work. They're proving things about convergence of optimization methods and so on. But it's also thrown up new formulations, and a lot of what I tell you in this talk are formulations that are coming from problems in machine learning that we have to figure out how to solve them using optimization methods. Some of these optimization methods are old, like stochastic gradient goes back, it's now almost 70 years old. Steepest descent, algorithms like that, you know, have been around for many, many years. Accelerated gradient's another example. That's almost probably 40 years old, and that's an algorithm that's very popular in the machine learning community. But there are also new algorithms that have been thrown up. So the algorithms that we use to solve L1 regularized optimization problems, for example, are fairly new. Okay. And so it's both new and old algorithms that are being re-examined and put to use in solving important problems in this area. All right, so let me talk about the basic setup that sort of applies to many of the problems I'm going to talk about. The typical situation is that you've got this big collection of data, and you can think about it as a collection of m feature vectors, aj, so j goes from 1 through m. And each of these, I'll think about it as just being a vector, right, of real numbers. And then associated with each feature vector, I've got some sort of outcome or label. I'll call that yj. So yj could be a real number, in which case I've got a regression problem. I'm going to try to use the aj to predict what the yj is going to be. It could be a label. It could be a label with two values, yes or no, positive or negative. Or it could have many values. For example, if you're doing speech processing, the aj might be just a 30 millisecond snippet of speech, and the yj could be the sound that you're trying to make. So the yj could have maybe a couple of thousand possible values. If you're working for Amazon, the aj could be something to do with your clicking behavior, and the yj could be what good do I recommend to you. So the yj could have literally a million possible values in that case. Okay? There could be multiple labels. There are also situations where there's no yj, where you've just got collections of aj. And in that case, you can still do interesting things. For example, the aj could all lie on some low-dimensional manifold, and your job could be to identify what that manifold is. And I've got an example of that later on. Or the ajs could fall into a fairly small number of clusters. And so your job could be to find the clusters that you can group the ajs into. And that tells you something about the structure of the data that would be interesting later on. Okay, so the fundamental task in data analysis, if I give you this collection of aj and yj, is to find a mapping from the aj to the yj. So I'm looking for a function phi, where I can plug in the aj as the argument of the function, and it makes a prediction of the yj. And my job is to try to learn what that function phi is. So given this collection of AJs and YJs, I'm going to try to figure out a value for phi, okay, in the function space that it lives in. Now, very often we parameterize phi. We define phi in terms of some vector of parameters, which I'll call x. And so the problem becomes to find the best value of x that will then define phi so that phi will do a good job of matching up the AJs and the YJs in the data collection that you're given, okay? So it becomes a data fitting problem, finding x to make the AJs and the YJs match up. And so we can build up an objective function that tells us how good a job is our value of x doing at matching the AJs and the YJs. So I can build up an objective function, and then the x that I want is going to be the x that minimizes that objective function. And very often this objective function has a special form. It's a summation over all the items in the data set. So it's often got this form of a sum from j equals 1 up to m, or some loss function, and the loss function tells you how good a job the vector x is doing at matching up phi of aj with yj. Okay? So the process of finding phi, the function phi, is what we call learning or training. Okay? Great. So given that we know this, we've learnt this function phi, what can we do with it? Well, we can use it to do prediction. So if I come along after I've learnt phi, if I come along with a new vector ak, I can plug it into phi and it will predict a value yk for the outcome. All right? And that's very useful. It can be used to do analysis. So by looking at phi and the structure of phi, it tells you a lot about the structure in the data. So for example, the phi tells you which components of the AJ feature vectors might be very long. They may have many, many components, but it could be that you only need to look at a few of those components to make a good prediction of yj. And the function phi might tell you which components you need to look at from the AJs to predict the yj. Okay, that's called feature selection. And that's very useful because it means that when you come along with a new feature vector, you don't need to know the whole feature vector ak. You only need to know a few components of ak to make a good prediction of yk. Okay? It might uncover some other structure like the low-dimensional subspace. Phi might tell you the structure of the subspaces that the AJs live in. It could find clusters, right? So even if there are no YJs, the phi might tell you which cluster the AK belongs to, right? So if by looking at the AJs you figured out that the data just groups into 3 different clusters, then when you come along with a new piece of data, you can say, okay, it belongs in cluster number 1, okay? And so therefore it will probably have similar properties to the AJs in the cluster number 1. So there are many, many possible complications here. There might be errors in the AJs and the YJs. Even after you've cleaned up the data, there might be mistakes in the feature vector. There might be mistakes in the class label, YJ. There can be missing data. I've got some examples of that where you don't have a complete feature vector. You only have some subset of the feature vector. Okay, and then there's this problem of overfitting, where it could be that you work too hard to find a match between the phi of AJ and the YJ, and you fit the training data very well, but when you come along with another piece of data that's drawn from the same distribution as the training data, but it's not actually in the training data, it may not do a very good job because the function overfits the training data. So this is still a very live topic, this topic of overfitting. And I'll hopefully mention it again at the end of the talk, because people are working hard on this problem of over-parameterized neural nets, which seem to overfit, but in fact they still do a good job of prediction, even though they overfit the data. And there's a lot of very smart people trying to figure out why that is. So this is still a live issue, okay? And we'll come back to it later. Okay, so I gave a talk about 18 months ago in Germany about this same topic of optimization and data science. And so I went to the web and I Googled cheat sheet machine learning. And you can still do this if you've got a laptop. You can look up cheat sheet machine learning. because I wanted to find a diagram like this where people could come along with a data science problem and they didn't know how to get started. They didn't know what kind of algorithms they should be using to analyze their problem. And this is one of the things that I came up with, and it's put out by a company called SAS. IBM has another one that's sort of similar. There's a number of these on the web. And the idea is you come in with your problem and it asks you some questions about what kind of data analysis problem you have. What are you trying to do? Do you have responses, sort of labels? Are you trying to predict numerical values? Whatever. And you're supposed to work your way through this chart and figure out, in the end, you end up in one of these rectangles, and it will tell you what sort of data science problem you have, and therefore what sort of tool you need to solve it. So it's sort of a decision tree or a flow chart for figuring out what kind of problem you have. And when I looked at this, I looked at particularly at these rectangles. And I realized that many of them were really optimization problems. The ones in the yellow here are really optimization problems. If you look at things like neural nets, or logistic regression, or linear SVM, or gas, you solve those using tools. Okay? And you could even argue that some of the red ones
I would definitely recommend you attending this
like
conference.
decision trees. People are using
really good evaluation
to find decision trees.
I think you will really like it.
MIT is doing that.
And
so at least
important
half of
links,
these things
the website,
make use of optimization, continuous optimization technology. So when I looked at this, I sort of realized that there was a lot of optimization going on
so basically,
across the whole area of machine learning data science. Okay, so now I'm going to go through a list of 13 problems
immediately you can go to
in data analysis, data science, machine learning,
and you can see
where
here
optimization is used. Okay, so I'll start off with the simplest one. This is the oldest one. It goes back now more than almost 200 years.
You can see the code,
and it's the classical. So in this case, the AJ and the YJ,
if you go to the processing,
I use the same notation as I had on the earlier slides. The game is that you want to predict the YJ by taking a linear combination of the elements of AJ. Okay? And the coefficients of that combination
and of course that has a
so you can think of this function phi that I'm talking about as just the inner product of AJ with X. It's the simplest possible function of AJ. Alright? And it's parameterized. And so you use that to predict the YJ. And you're trying to choose the X so that it does the best possible job of predicting the YJ. Okay? And one way to do that is you take the difference between AJ transpose X and YJ, you take the square, the positive number, and you sum those all up over all the items. And then you just take the X that minimizes that. Okay? So this is classical linearly squared. And we thought, when I was in school, which is now 35, 40 years ago, we thought this was a solved problem. Right? This was a classical problem in numerical analysis. People knew how to solve this by factoring the matrix A or by doing conjugate gradient or something. But nowadays, if you go to URIPS or ICML, you'll find that people are still writing papers about this problem. Okay? And what's different now is that the dimensions have gotten much bigger. You know, M is now in millions or billions. The length of X might be 1,000. So the problems become very big. And so people are using things like stochastic gradient to solve this problem, which we never would have dreamed of in the old days. Okay? So this is still even though it's very old. Okay? And there are some modern twists on this. Well, not so modern anymore, but people do things on this problem to sort of change it a little bit, to change the properties of the solution. So there's one technique that goes back to the, I think to the 70s, particular regularization, where you add on to this objective, you add on multiple of the square of the 2 norm of X. Okay? And by setting lambda to some positive value, you get a value of X that's a little bit lower. Decreases the norm of X. And that tends to improve under certain assumptions. It tends to make the X less sensitive to the noise in the Y. Okay, so if there's some errors in the Y, some Gaussian errors, or then by adding on a term like this, you get a solution that generalizes that to unseen data. it's less
and then
sensitive to those errors.
you can directly
And then recently, this is more a more recent innovation,
usually very fast,
is to add on a multiple one norm.
you can also set here to find.
And this gives a solution where X now contains a lot of zeros.
We have a very dynamic form.
And in fact, as you increase the value of lambda, X has more and more zeros in it. It gives you a sparser and sparser vector. And why is that interesting? Well, it's interesting because if you've got a zero component in X, it means that it doesn't look at the component of A. So when I'm forming this inner product, the zero components of X, that means you completely ignore the corresponding components of AJ, right?
And if you want
the only
also
thing that affect the
parts, you
inner
have now
product
to
of
install
AJ
also
is non-zero components.
That's all it's needed.
So this does
So the days
what
that
I call
was come together to install,
tells you
no more,
which
that's
elements
all
of the
the
AJ
installation is very easy.
to predict the YJ.
And then you can write your own
So that's
scripts.
why this sort
you
of
can connect to the notebooks.
the whole area of
all the
compressed
standard
sensing
things that
is
that
founded
now
around
are
software
available with Python.
that
And you can
feature
study the
selection, that
API
sort
and look at
of
it
do compression
and go
on
into
the
it
data
in
and so on,
details.
which is
Something else we're providing,
Okay, so that was the first
datasets. That's
application. Here's the
something
second one.
also
It's kind of a
relatively
variation
new now.
on that.
We are collaborating with MGA.
You're still using AJ
with
transfer
some labs
predict
in
YJ.
Denmark and so
But
on,
now
different labs,
you might
and
use
they
a very,
provide
instead of
datasets
using the sum of
for
squares
that,
loss
which we
function,
allow
you might use
people
some other
to
function.
write a command line
It might even be a
and
non-convex
fetch datasets,
And why is that
specific
useful?
datasets that they want.
Well,
Single cell,
the
multi-cell,
reason people use the sum of squares function in the first place, or
with
one
the double
reason,
diffusion
is
encoding,
that
we
it
have a
works
range
well
of
if you've got
datasets
Gaussian errors
to
in
provide
YJ.
templates,
Because this is the
and
maximum
you can
likelihood
just
function that you get
fetch them in,
if you
download
assume that
them
the
from
errors in the
command line.
YJ are Gaussian and you're looking for the maximum likelihood.
And run the
Now,
run your
often that's not
experiments
a
with-
good
with
assumption. Often the
existing
errors in the
datasets.
YJ are not Gaussian,
All
they're
right.
some other distribution.
Also, something that is new in
And
that
the
by
problem
one,
with using this
before in that
sum of
by you
squares
had
is that
to
if
do
there's a
Python.
big error
You
in the
had to do
YJ,
Python.
it tends
Now,
to give a very big value
you
of
can,
the square, and therefore it will have a big effect
just
on
use command
the
lines.
Right?
So we have a system.
And so people sometimes use
that
these
we
other
call guide by
kinds
workflow
of
system
loss functions so that
takes
if
Python
there's a
code,
big error in the YJ, it doesn't
you
have
write
such a
some
big
simple
effect.
Python code like that, and it
So there
creates
are
a
many
command
variations of that, but here's one of them. It's
command
called
line
2D
interfaces.
byweight.
And now we
And
have
this
already
function, it looks like the
20,
least squares function
command
if
lines.
close, if theta is
Soon we
close
will
to
have
zero.
hundreds
But
of
as you
command
get
lines.
away
So
from
people
zero, instead
who are
of growing
used
infinitely,
to work
it flattens
with,
out, asymptotes at one.
with command lines
Right.
from the terminal.
And so that means if there's a big error, if AJ transpose X minus YJ
like
is
something
very
like
large,
this,
it doesn't have such
we
a big
provide
value.
that.
And
Which
therefore
we
it
will
doesn't
not
have such a
provide
big
before.
effect
So
on
this is
X.
something new.
So it's more robust to large errors in the YJ.
And also what is else that we new, we
You
have
can also
also
use,
now
instead
web
of using
interfaces,
the 2 norm or the 1 norm
there is a
here
collaboration
for this
with
regularization term, you can use
Brain
some other
Life.
function,
BrainLife.org
such as
is a website
these
where
functions
allows
called
you
scat
to
and
run
FTP. So these
pipelines and
functions
commands
here
online.
were invented in
So
the
we have many
maybe
drive-by
about 10
apps
years ago,
available
and they look
online.
like
So
L1,
there you can
so
upload
they
your
look like the
data,
absolute
private
value
or public,
function,
and
but
then
instead of growing
run
to
an
infinity,
existing analysis
they
without
flatten
even
out. So they
writing
start out
command
like
line.
that and then they
So
flatten
like
out like that.
fancy web.
So once again,
So.
you don't incur such
But
a
for
big
people who
penalty
are
if the
working on
component of X
methods,
is large.
you should get
Instead of having a big penalty for having a large X
look inside
component,
in the
you only
code
pay
base to
sort
see
of
what
a
you
fixed
can learn
price. Okay?
and use.
So
Okay,
these
so
functions
now
work better
I'm
if the
going to
errors
switch
satisfy
to
certain kinds of distributions.
more
The problem is that they're a little bit harder
so you
to
have
optimize.
seen
These problems here are convex.
you have seen maybe images like that.
So they're relatively
Here is
easy
what
in
is the
some
real
sense to
brain.
solve.
There are
These
some
problems are non
pathways, some bundles
and so
here.
they can be a little bit more
And then
difficult to
here
solve.
what we can
They
do
might have
with
local
diffusion
minimums.
MRI, we can reconstruct
Okay.
some
But
of
there's
these
still optimization
pathways
problems. As you can see, it's a minimization over here.
with computers and
Okay,
with
number
MRI.
3 is so-called
but then
matrix
there are
sensing or
multiple
matrix
issues
completion.
there that need to be tackled.
These problems became
And
prominent starting
how
maybe
to
about
make a really- how
12
to
years
make
ago.
this transition
Papers
really,
by Fazel, Candace, Perillo,
accurately
Wright,
is
and so on.
is
And
not
this is
really a
basically
problem.
like least
And I
squares,
have
but
been
it's
looking
applied
into
to
this problem
matrices.
from my
Instead of the
PhD,
X being a vector,
until
it's
today,
now a matrix
and
of
trying
some
to figure out
size,
how
n
this
by
can be
R
done.
or n by P or something.
So
And
I'm going to switch
now the
now to another
YJs are
topic.
observations that you're making about that.
and explain you about
So
that.
these AJs, instead of being vectors
Alright,
now,
so,
they're linear operators on the matrix. So they're the AJ of X is some combination of the elements of x, okay? And what we're told is that a certain combination of the elements of x gives you this outcome yj. And by looking at multiple such observations of the matrix, you've got to figure out what is x, okay? And very often you're given some additional information about x. Like you know that x is, for example, a low rank matrix. And that extra information gives you the ability to recover x from these collections of observations. So it's like least squares, but it's applied to matrix problems.
So
matrix
if you have ever done tracking,
so
when you
this
finish
earliest
with
paper in this
tracking,
area by Wright and
you get
Perillo,
millions of streamlines.
they use this fact that x
And there are multiple papers that have
is low
shown that
rank
many of those are
to
invalid.
recover it in a provable way
Some people
by
say
adding on
60%
lambda
say
times
60%, some people say 90%.
this nuclear norm is
invalid.
like the L1 norm of a
And there were some papers that were a bit,
except that when you plug in a matrix, you sum up the
let's go
singular
with
values
negative.
of the matrix.
And
it has the same
about
effect as the
cartography.
L1 norm. It tends to give
For me,
you
cartography is
solutions
exactly the
where the
opposite. There are
matrix
some
is
issues, but it's
rank.
actually a good field to be in,
So
and there is
more
a
recently,
big
people have
challenge.
been finding
but,
other ways to formulate this problem. This
you get
obviously
that.
is an optimization problem.
So
But recently, people have been
you
building
have
in the
all
low
these
rank
streamlines. What do
structure.
you do?
So instead of solving this for x,
Because there's
instead
going to
you
be some
say,
that
let us represent x
are
by the outer
atomically relevant,
products,
and
two
some there will be
matrices,
noise.
L and R.
Right.
Okay, so we represent x.
And then
as the
also
product
let's
of L
let's
times
also
R.
think about why to use
These are two
streamlines.
thin matrices.
Well,
And you choose the width of these
basically,
matrices to match the rank
streamlines
of x.
are useful because
Now,
you can
the
represent,
problem with this,
you
the
can integrate
advantage is
information
that it
along
can
many
handle a
voxels.
much bigger problem.
They have
Because
some
if X is a
connectivity
very
SQL
large
information of connectivity.
Like with
They can provide
billions of
some
entries,
description about
this is a
shape
very
and
difficult
orientation.
optimization problem. Just because
They make
it's so
good
big.
models of bundles when
But
you
if
put
the
them
matrix
together,
only has rank 3 or
of
4,
tracts.
then the number of
course, there are
unknowns in this
approximation.
formulation is much smaller.
But
It
they
might
have
be smaller
multiple
by a factor of
issues.
1,000
So
or 10,000.
usually in
And so you
imaging
can
it's
solve
about
much bigger
images.
problems with this formulation.
But then when you
The
start getting
difficulty with it is it's
those things, those are streamlines.
Okay. This
and
one
we're
is
not
convex,
really
this one
used
is
to processing streamlines.
Because if you
in
look
imaging.
at the unknown
Because we use
L
in
and
images.
R,
And those are
and if I
different.
fix the L, then it is
animals.
convex in R
So,
alone, but it's
for
not
example, a
jointly
simple
convex in
problem
both
you
L
will
and R.
face is the
So it's
order of
not so
streamlines.
clear that if you apply
Some streamlines could
problem
be
by
saved
the
with this order,
global.
and some of them could be saved
We'll return
without
to this
order.
later on,
So
because it
starting
turns out
from
that
the
even
end
though it's not
first, and
convex,
then from the
people are finding in
what
practice
looks to
that it
you
does
as
find
end
problems.
could be the beginning and
And
the
now
opposite.
there's some
So
explanation
then you
as to
must
why
be
that's
careful
true.
if you compare these
We'll
two
return to
streamlines
that.
now, not to
I think
compare
it's
this
just
point and that point.
Okay, here's a
But compare this
variation
point and
of
that
what's called
point.
non-negative matrix factorization.
Because
This is
maybe you
become
want to say
important in
that
certain
this-
applications like
These two
computer
maybe
vision,
they belong
document
to the same
clustering,
class, the same
chemometrics,
group.
and so on. There's been a whole community of people in those
And
areas.
to
that
compare,
worked on this
compare
problem.
those is not
Even
anymore like you
prior
have a
to
pixel or a
10
voxel and then it's
well,
just a
optimization,
neighbor
people got
of
involved.
that voxel.
So the
Now you were
problem
thinking
here is
about neighbors
that
of
you give me a
streamlines. What
matrix
means a
Y,
neighbor of a
which
streamline?
generally has all positive entries.
So you have to
Okay.
think about
And
distances,
you want to
define
find
distances
matrices
that
L
work
and R,
with
which
streamlines.
again are skinny
And if you
matrices,
look at
very
that,
thin
You
matrices.
can make a very small
so
experiment,
that
have
L
1 million
times R
streamlines,
transpose is
and try to
approximately equal to Y.
take one
So
randomly
you're trying to
and
find
try
a low
to
rank
find the
approximation
closest,
of Y,
think
but
of
also
the
you
way
want
to
the
find the
entries of L
closest
and R to be
streamline
negative.
to that spaghetti
So
of,
you essentially
of
have this
streamlines in a
constraint
tractograph,
optimization
in
problem.
tractography.
Again,
You will see that
it's
computationally it's very
not
heavy,
convex.
very heavy.
It's not
So
convex.
one thing of the day
If I fix the L,
think
it's
about some
convex,
fast
convex
distances.
in R. If I fix the R, it's convex
And
in L.
there is a
but
way
it's not
to
jointly
think of
convex in L and
streamlines
R
kind of
together.
like vectors.
Okay.
And
However, people
then
find,
you
in
can
fact,
have
the way
a
that
very
people
fast
solve this
distance.
problem, almost always, and it still works
So
very
basically,
well, is so-called
you try to
alternating.
get the direct Euclidean
Well, they do
distances
exactly
from this
what I
point.
say.
You get in fact
Make
the
some
average
guess
for
about
that.
R,
And the average,
fix
and
that
the
guess,
average
and then they
think
solve the
that one
problem
of the
for
two
L
streamlines
with a
is
fixed R.
flipped.
That's just a constrained least
And
squares problem. So
that
that's easy to
was
solve using
much
gradient
more
projection.
efficient
And then
than
they take that
using
value
standard
and
methods.
fix it,
Maybe
and
you've
then
heard
they
about
solve
it
the problem
using
for R,
Hausdorff
and that's
distances
another
and
constrained
so
least
on,
squares problem.
that the
right?
complexity
They find a
is
new
much
value for
higher.
R. And then they fix R and go
And
back.
also
and
it's
solve that way.
easy to calculate.
So they do this
centers in
so-called
this
alternating direction. They
So
alternate
the
between
first
L and R.
distance
And that's a very effective
introduced was minimum average directly.
It's hard to
This
guarantee
distance,
that
which
it
is
finds a
you
global
calculate the average of
practice
this
seems to
Euclidean
work very
distances
well.
here. And then you
Okay,
take the
here's
mean
number 5, sparse inverse
of the
covariance.
sum
This was
of
invented
the
back in
average of these two
2008.
averages.
So
And we
Alex
found that actually this is a proper distance metric for the mathematicians here.
This is one of the
proper
first really
distance metric.
successful applications of
It
optimization
satisfies,
technology in data science, I would say.
Many
This is one of
different
the best papers.
symmetry and different equalities that you need to create proper metric space.
10
And
or 2009.
it has one small
long time
disadvantage.
ago.
It means that
Anyway, so
its
what's the
streamlines
story
have the
here?
same number of
So the
points,
story
because
here
the
is we've
streamlines
got
could
a
become
vector
different
random
numbers of
variable.
points.
So Z is
But
a
that is
vector
also very fast and easy
of
to
length
compute.
P.
You
It's
just
a
set
vector
the
random
specific
variable.
number of points.
So you can make multiple observations of this random variable. Okay? Now the
Otherwise,
elements of this vector are not
people
independent.
work with very
So for
complicated
example, the
distance
first
they
element
use
of the
spectral
vector and the third
analysis,
element,
O'Donnell-
they might be
Lauren and
correlated
O'Donnell
in
had
some way. They
famous
might tend
methods
to go up
doing
and
that.
down together.
But
So different random
they would always work
observations
with
might be
small
related.
number of streamlines, let's say 10,000.
And you're going to make a whole lot of
I wanted to
observations,
be able
say
to
n
work with
observations of this
hundreds
vector.
of thousands of
And you're
streamlines,
trying to figure
millions
out
of
what are the
streamlines, because that's what the
relationships
data were
between
coming.
different components.
They were coming now to become bigger and bigger
How are
and
they
bigger, so
related to each
people
other?
couldn't like analyze
You
it.
can do that by
So
forming
then the
simple
paper,
covariance.
I wrote quick bundles and
So you can
methods
take
for
outer
photography,
products.
it's a
Each of
process
these
simplification.
observations are called
Was the
ZL.
idea, okay, let's use
I
this
can
fast
take outer products,
streamline
ZL,
distances
transform.
and do a clustering
I
that
can
is very
sum them all
fast,
up,
and let's
form
see
sample
how good the quality would
Okay.
be.
And that will tell you how the
So
different
quick
elements
bundles
of
is a method
vector,
for
random
fast
vectors are
clustering
correlated.
to build clusters.
But you're asking a more complicated question. You want to know which entries
And
of,
here
sorry, which
how it works.
relationships between the
The
entries
algorithm
of Z
is very simple. You
can
have to
only
assume
be
already
explained
that you have a distance
by some sort of
that
direct
you can use as
equalization
the
between the
MDF
two.
distance.
In other
But after
words,
you have
I
this
guess I can
distance,
illustrate it better with this
then
picture.
here
Suppose
is
Z has
how
6
the method
entries.
it works. I don't have the
And if
the
in this
pseudocode
chart,
of the algorithm, I
the
will show
lines
you the
between the
algorithm
different entries of Z tells
visually.
you
It's
which
very
ones are
simple.
directly influencing
The idea is
the others.
extremely simple.
So, for
And now
example,
this
there's a
method
line here
is
between
used
3 and
also
5
in
that
other
says
things.
there's a direct relationship between the third and
For
the fifth entry
in computer
that
vision,
can't be explained by
in
a chain
GPS
of
tracking,
relationships with
and so on.
other entries. Okay?
But
So
imagine you have
3
this
and 5
streamlines
directly
here.
affect each other.
Okay,
Now you'll also
imagine
find
you
if you
have
look
this
at
streamline.
the sample covariance matrix,
If
1
I ask
and
you,
5
how many
will also be
clusters
related
did you
to
see?
each other. They'll tend to be correlated.
What
But that correlation
would be
can
your
be
answer?
explained by this chain of relationships between
So
1
someone
and
said
2, 2 and 4,
1. Okay, someone said
4 and
1.
5.
Someone said 3.
And also between the
3,
chain
okay.
1 and 2, 2 and 3.
You say 4, okay.
In other words,
4.
I can explain the
anybody
correlation
else?
between the first and the fifth entries
Well, you have
by
1, 2, 3,
a set of other
4,
correlations.
5.
But the correlation
streamlines.
between 3 and 5, I can
So,
only explain
okay.
it partly by the fact
So,
that they're directly.
if you know about clustering, you know the answer is
Now, through some magic
like,
of
that there is
statistics,
no answer.
these direct
Because it
relationships are
depends on
revealed
the
by
level.
the inverse of the
You can see all that as one cluster,
So if I take this
Or
sample
you can
covariance
see it
matrix and find its
as
inverse,
a different
that
number
will
of classes.
tell me which entries of
But
that vector
let's
are
say
directly
for humans, what would be the
Okay.
easiest? Like if
And
you
so,
start saying,
what's the
I will show you
optimization
what
problem
it
here?
is.
The
I will tell
optimization
you
problem is
what is the
to
answer,
find
okay?
a matrix F
But I can tell you
that's
everything, it's
approximately
very hard to see
the
what's
inverse of
happening.
S, and that
What are
also
the
is sparse.
classes?
Okay?
Okay.
Because
However,
the
some
non-zero
have
entries of
the
X
right
will tell me which entries
One
are
of you had
directly
the right, I
affecting
think it
each
was.
other. So you can see that
so
in
well
this,
done.
this picture here,
So
each of
imagine
these
we bring
lines,
randomly
each of these
one
arcs
student,
correspond
okay?
to a non-zero entry in the matrix.
And okay,
So for
this
example,
we call
there's a
this
non-zero
now
in
the first
position 1,
cluster.
2.
The first cluster
That tells me
as a
there's a-
centroid,
there's a-
as a representation, that's it.
There's a 0 in the
That
entry
becomes
1,
cluster
6.
1.
That tells me
Let's
there's no
now
arc.
pick another random.
Okay? So here's the
streamline.
optimization
This other
problem.
random streamline
We find a matrix
is,
X that's approximately the inverse of X
looking
of
quite
S
different
and is also sparse.
from that.
And
which
here is the
that one
problem
here,
that's
which
solved.
better.
It's kind of
And
complicated.
if you
We plug
calculate
in the S, we
the
take the
distance
inner
using
product between S and
MDF,
X, we
this
subtract off
method,
the log of the
It's
sum
quite
of
different,
X.
like all these points are all
We
quite
add
far
on
from each
lambda
other.
times the
It's
one
quite
norm of X.
So you can
and
think
we
of the
find the
distance
X.
threshold now that we use. It's a parameter
If
of the
I
algorithm.
leave off this last term,
And we can
the
say,
lambda
okay,
term,
that,
I just
okay
set
according to
lambda
that
0.
threshold,
The
these
minimum
two are
of the first
some
two terms is just
different.
S.
So we have now a new
So if
cluster.
I don't do any
And you have a
regularization, I
central
just get
from
the
that
exact
cluster.
inverse of X.
Then
But
we
if I
pick
add on
another
this term,
random
it tends to
streamline.
give me an X that's also sparse.
This one looks
And
definitely
it's the
different from
sparsity
the
that
first cluster.
reveals
The
the
one.
structure of direct causal
And
relationship
looks
between the entries of
also
Z. So it's a
quite
really
similar
beautiful
now
application of optimization technology
So all the
in
small
solving
distances now here
really
between these points will be small.
Okay.
Okay.
So that was number
goes
5.
to the second cluster.
Okay, number 6,
And
sparse PCA. It was
then we
actually the
have
same people, Gaspard Martin
another
and
streamline here.
cohort,
Looks pretty
that
different.
used semi-definite
than
programming
the first
technology or
class centroid.
optimization technology
This
to
is
solve this problem. So in statistics,
looks
again,
pretty
given the
different
samples
also
are very
from now the
geometric,
centroid
statisticians are very interested in finding
of the second
the
class.
leading eigenvectors and the leading eigenvalues of this
The
matrix.
centroid is being
Because by finding
created
low-rank
dynamically.
approximations,
So then it
of
becomes a
this,
third cluster.
it sort of tells you what
And
are
there
the
is
most
only one
important
streamline
directions
left,
of
which is this
variance
black one
along
here.
which these,
Which
along
we
which
pick it
interesting
up.
things happen. And they're the
And
leading
that one,
eigenvectors and leading eigenvectors.
Of course,
leading
looks very similar to cluster 1. So we'll go to cluster
But they
1.
want to go beyond that and
So at
they
the
say,
end,
give me an approximation
we
to the
try
leading
with all
eigenvector
classes,
that's
and
also
at the end,
sparse.
the closest
So they say,
distance
let's find a V
to the cluster
so that
centroid
V
is
transpose
cluster
S
1.
times V is as big as possible.
So it
V
goes
has a normal
to cluster 1.
1.
Question,
So
okay,
it's
go
not
for it.
trivially like doesn't go up to
It's
infinity.
fine.
But also the number of entries in V is less than K. The K might be 5 or 10.
Okay, great question.
So give me a sparse vector
What I have seen
with only a
is
few
there are
non-zeros,
specific thresholds
unit norm,
that
and it
work
also has maximum.
For humans, for
product.
example, if you take
Okay.
your cartogram
So
in MNI,
that's an
like in
optimization
MNI
problem,
coordinates or in
hard optimization.
what is called
Because this is hard to
wall
represent
coordinates.
as a constraint in optimization.
then
Number
the
of
threshold
non-zeros
is
in the
you can
vector.
use like 10
It's
and
hard to
15
do
and
that
you're good.
without bringing in.
So the
different
threshold
variables into the problem.
is in millimeters.
So they came up with this
And it has
realization.
a
They
meaning.
said,
It has
let's
actually,
not solve this for V. Let's replace
It means
V
that
transpose by some matrix
If I have two streamlines
And let's solve
in
the
the
semi-definite
wall coordinates,
where
or
M is the
scalar
unknown.
coordinates,
It's now an n by n matrix.
already you are
And
in
I try to
millimeters.
maximize the inner
This is
product
for
of S
humans.
and M.
Then if you
M
have
has
two
to be
streamlines
positive
like that,
definite because it's
that is
representing
0,
V transpose.
the
And
base
it
goes,
has to have
and then if they start opening,
trace. So if I sum
then you
it
start
back,
going like 1 millimeter, 2 millimeter,
1.
and so
But now
on.
let me
And
put a
depending on the
restriction on
angle
the one
also,
norm
there's
there.
going to be some deviation.
Now that
But
sort of has the
they
effect
mean something.
of forcing M to have
And it's
low
important
range.
to have a
So
threshold.
they impose constraints
Yes.
to try to make M have low range. And hopefully what they end up with is a range 1 sparse matrix, and then they can figure out from that what the so if I give you a rank 1 sparse M, you can factor it.
Yes.
So that was the innovation in this
algorithm
paper, so they wrote it down.
Is order dependent. If you have
The disadvantage of this, so this
if you
works,
have clusters that are
prove
really
that it works in certain
really close to each
situations.
other,
The disadvantage is that you're
like,
replacing a
there
difficult
are no gaps. If there are gaps
There's only
between
n
clusters,
variables in
it
the
will
first
work with it.
problem,
But if
but
there
it's
are,
hard because
then there's going to be some order.
they're replacing with a convex problem. But the convex
yes,
problem has many
but
more
I will
variables.
tell you
It's
how
got
you
n
can solve
squared
it.
variables.
Now remember, when I built
So
that,
n is like 10,000.
my primary concern was
This
speed.
problem has 10 to the 8 on
Get
it.
something,
So it's
get
much
a
more
reasonable
difficult
result
from that point of view.
as fast as possible.
So nowadays
That's why
people tend to
quick
shy
boundaries,
away. They don't tend to use
Um,
formulations like this.
So
They go
here's
back
how
to
it
this
looks.
problem and
Let's
try
say
to think
if you take
of an
this
explicit
bundle
way to represent
and
this
you
constraint.
class it with two bundles. I don't remember the threshold I just did here. Here are the
So,
centers of the class. Of the classes.
So they
and
tend
here
to
are the
work a lot
classes
more with
with
this,
different colors.
but they come up with,
What
for
we
example,
can see,
constraints on the one norm, for example.
Is, for
and,
example, although
try
you
to
feel
solve
that
the problem
this
that way.
streamline really goes, this bundle really
Okay,
has streamlines that go
this
from
one,
here and
robust
up here.
PCA. I called it 6.
In
I
reality,
cheated and put in
there
one
are some
more
very strange
formulation
streamlines
last
in this,
night. So I've actually got 14, not 13. So
CSV,
this is like the 7th
this called
one,
cosine type.
6A.
Look, there is
So this
one
is a
that breaks up
variation on
here
the one
very early.
before, where you're given a matrix Y.
And there is one that
And you
starts
know
from
that
here.
it's a
There is also a
combination of
crooked
sparse
one
matrix
that
and
goes
a
up
low
and
rank
then
matrix.
goes like that.
So the low rank part I
Which,
represent by M,
it's unexpected.
like on the previous slide.
Anatomically, it's unexpected. So already, although
the sparse
we
part,
didn't put any information about anatomy, you start getting something
So you can
about
recover
the data.
this
Just
by
looking
explicitly
on those
representing
classes.
M by LR.
And here is
I used that trick already.
video.
I explicitly write the low rank matrix as a product of these matrices, and I leave the sparse part alone. I represent it like this. But I put
Yes,
a
so
penalization in the objective function.
This is an example with a billion now cartography.
The one norm tends to give you back
Streamlines are being randomly.
zero entries.
Then the
So
centroids
this
are being
the purpose
updated
of this
dynamically.
term is to induce
Here.
sparsing.
And then you will start seeing
so by finding an L and an R and an S that minimizes this, I do a good job at fitting the Y, the data in the problem, and I get back a low rank part.
This
has a really cool application in video processing. So if you've got a surveillance video of a bank, for example, of the lobby of a bank,
so then you will see some
the video runs for many hours, it's got many frames in it. There's a low rank part, which is the part that's the same in every frame. So the furniture and the carpet doesn't change from one frame to the next.
I would like to have an animation that works with 1 million frames to show you that, but then visually you cannot really see it. We need a cave or we need a virtual reality.
So they're the changes that happen occasionally.
But it's the same principle. There is a question.
And so that's a classic example of how you decompose many frames of video into low rank stuff, which is always the same, and the sparse stuff is stuff that changes just occasionally.
No, there is no box.
Okay, this is the one that I added last time. This again is a classic problem in learning, where you're given a bunch of data, typically a very big matrix, and what you know is that each of the columns in that matrix can be represented as a combination of just a few elements in a dictionary. So there's some unknown dictionary out there. Might have a lot of entries in there.
The length of the stream line does not need to be the same.
Can be represented as some linear combination of just a few elements.
On a streamline,
so you're trying to find a dictionary.
The same. So there
and
is
you're also trying to find the coefficients R that give you X. So you're trying to find the D in the R such that D times R is approximately equal to that.
And we know, for example, if you have 20 points,
so the unknowns in the problem now are both D and
per streamline,
data is X.
So you have like 20
in some problems you know a priori that
the geometry
D has
is pretty good. You don't lose much.
columns of D.
If you need more accuracy, you can go up to 100
I don't know
points,
much about the application.
That will make
I'm told that this is an interesting problem. So in that case,
but
you can
those
take this thing that
if you're familiar with functional analysis or with Fourier analysis,
D times R, multiply by D transpose, and you find that D transpose X is approximately equal to R. And so now you can say, well, I know that R is 5, so let me find D
and so on,
such that D transpose X is 5,
from having like 1,000 points for some streamlines,
but D transpose D is identical.
Well, 1,000 points for the long ones and 100 points
so let's find D that solves
20 points.
Once I've got D, I can recover R by going back to this formulation.
Okay.
So people have been solving this
Thank
problem.
you very much for the question.
An optimization problem. It's kind of a hard optimization problem because the constraint is a manifold constraint. Right? The unknown is the matrix D, but the constraint is a manifold.
So what you get is
the
for
objective function
you will get something like
is also a little bit
classes.
tricky because it's non-smooth.
But think about that. From 1 million to 4,000.
So one way that people go
good.
about this is instead of trying to find the whole matrix at once, they try to recover it one column at a time.
Of the
So
data.
they say, let's just try to find one column of D by solving this problem.
So it's what is quick one is a
this
fast
problem's
way,
a little bit easier, but it's still
fast supervised way
problem because of this constraint here. This constraint says D has to be on the surface of a ball.
And
it has to have unit norm. And the surface of a ball is a
take out some of the
set.
computational load.
The ball is a convex set, but the surface
is really something. It's a base.
So recently we've been trying a bunch of different approaches.
But what is not quick balance is not a way to find anatomically relevant, exactly anatomically relevant white matter.
Take steps and project back onto this surface.
So it's not something that you ask in your anatomist to
all of these are kind of pretty effective methods.
And then you run with one success. Exactly that is the same with what. No, some of them they will be similar, but that's not the idea. The idea is to reduce the complexity.
Okay, I'll do one more and then we'll have a break. Okay? So, subspace identification.
Right.
So in this case, this is an example where there are no wide data. I just got the data collection consisting of the AJs.
And
in this case, in this particular application, the AJs are equal. So this is a problem in so-called structural motion. You're making observations of an object that's opaque and you can't see through the object. It's not transparent. And so when you take a picture of the object,
the number of clusters is small,
the reference points on the surface of the object
on average it's linear time on the number
So each observation is
and
a
if you have
projection
started
of a
classing,
bunch of reference points onto a plane.
and you know other methods
you're able to
that
take
you can
pictures
get into
from
linear
different
time classing, let me know,
Okay,
because they're not
so you've
many.
got
Most classing
projections
algorithms, they start from n squared
of the surface
or
of
n
the
z.
object. And given enough projections, you're able to reconstruct the whole
Now,
surface.
if the
So this turns out to
threshold is
be
very small, that
a
means
so-called
also the number of
subspace
classes is very
multiplication
small.
problem.
Then
Each
the
of these
complexity
AJs
goes
is
to
a
be
projection
worst
of the
case,
surface of the
worst
object on a
case would be
particular
n squared.
plane.
But you never really,
And it
I
turns
never
out
really
that
use, I never
all of
really
those
go there.
AJs lie in a rank 4 manifold.
To have
rank
like
4
as many,
linear
because
subspace.
then it's like
And so you
you
have to
want
identify
class
what
1
that
million,
subspace
million
is.
statements, and then you
That's
generate
the
1 million classes.
Once you know what
Doesn't
X
make
is,
sense.
you're able to reconstruct it.
Okay,
So this
So
is an
the
actual
idea is
experiment we did in one of our
divide and conquer.
The thing
we
that makes
start
it
from
tricky
big
is that
thresholds, and
you
then
can only,
we
you
build
can't
trees,
see the entire
and we
vector
class
AJ.
again
You
at
can't
smaller
see the surface
thresholds.
of the object that's
So we
on
have
the
a
side.
layers where you.
So each of
We
these
know
vectors
that for
AJ is
when you're looking at few classes,
missing
quick
it.
bundles is very fast.
But even
So
despite
we do that, and
you
then
do a good job of reconstructing this matrix X. Okay. Let's have a break for 2 or 3 minutes. Okay. So you can write down, how do you find the X and the beta, which define this plane? You can write it down as an optimization problem. So you can take all of these conditions and write it down as a minimization problem. So if all of these conditions are satisfied, this function has the value 0, okay? But if any of these conditions are violated, there's going to be a positive value here. And so by choosing the X and the beta that minimize this function, hopefully we'll find the plane that does the best job of separating the two sets, okay? Now you can also add an extra term on the end here, lambda over 2 times the norm of X squared. That tends to give you the value of X that does the best job, that has so-called maximum margin separation. So if I look at this solution here on this picture, this hyperplane is okay, gives a 0 error, but if the data points are drawn from these two distributions, the red and the blue distribution, you can see that the plane doesn't do a very good job of separating the two distributions because it cuts off some of the blue distributions on the wrong side of the plane. This plane would be better, okay? The one that so-called maximum margin plane that goes down the middle. Now sometimes, and so if I go back to the formulation, if I go back to this formulation, if I add on this term, it will tend to give you the maximum margin. It will tend to give you this solution that has the maximum distance from the points, okay? And so it has a better generalization property. Now sometimes you get, of course, in most real-world problems, the two sets are not neatly separated like that. Usually the two sets are somehow a little bit mixed together. But even when that's true, you can still solve this problem and find a hyperplane that does a pretty good job. Now it will have a positive value of H at the solution, but it will still do a pretty good job of separating the two sets, like here. Okay? So that's linear SVM. So here's number 10. This is kernel SVM. And as I said, in the 80s and, in the 90s and early 2000s, this was the most popular form of machine learning, I would say. And the idea here is that you don't work with the raw vector AJ. You actually do a transformation of AJ, usually into a high dimensional space. So I do a lifting of AJ, I apply this transformation psi. So psi is a mapping of AJ, usually to a high dimensional space. And then I do linear SVM in the high dimensional space, okay? So now my function phi, I get by taking psi of AJ transpose X minus beta, okay? So everything here is exactly like the linear case, but now I'm working with a transformed version of the AJ. And with this transformation, I can do much more powerful separation. I no longer have this situation where the AJs might mix together. I can lift the AJs here from a 2-dimensional space to a 5-dimensional space. And if I do the lifting right, I can find a plane that cleanly separates the two, okay? So I can solve this optimization problem here and get an answer. And it's just as easy as the previous one. It just has higher dimension. But the brilliant observation that these people made was that if I take the dual, this is a quadratic program, I can write this as a convex quadratic program. If I use duality theory from optimization, I can write the dual of this problem, and it has this form here. Okay? And this matrix Q in the dual turns out to be the inner product that I get by taking two different feature vectors, AK and AL, doing the transformation psi, and then taking the inner product of the two. That's how I get the entries of Q. And these are the people that figured that out. And they made this observation that if I work with this formulation, I don't actually need to know psi. I don't need to explicitly define the transformation of AJ, because all I need to do to solve this problem is to figure out what the Q is. All I need to know are inner products of the psi with itself for different values of the feature vector. And so they sort of bypassed this problem of defining psi. They said all I need is a mapping K, which takes two feature vectors and produces an output. And so they work with this K, which is the so-called kernel. It takes two features as input, it produces an output that you can use to construct the matrix Q. Okay? Then when you solve this problem, you get a vector alpha. It's a bound constrained quadratic program with an extra constraint formed from the labels Yj. When you solve this, you can then use that to form, to get predictions from other feature vectors. So when I come along with another feature vector, I can use the solution alpha to make a prediction about the label Yk that belongs with that feature vector. Okay? So that was a really beautiful use of optimization ideas, particularly duality theory. It also gave rise to a problem that you could solve very efficiently. And for a long time, as I said, this was the most powerful tool in machine learning, one of the most powerful tools that was out there. Okay? Now this is just for two class problems. Let's sort of generalize this to multiple classes. So there's this area of logistic regression, which again is a very classical tool in machine learning and statistics. And the idea here is that you've got multiple labels. So no longer do I just have red and blue. I may have Yj can take one of m possible labels. And now I'm not just trying to make a prediction of which class Aj belongs in. I'm actually going to try to give you odds. I'm going to try to tell you, if you give me a feature vector, I'm going to try to tell you there's an 80% chance it's in class 1, and a 5% chance it's in class 2, and a 12% chance it's in class 3, a 1% chance in class 4, and so on. So I'm actually trying to make a prediction of all the odds. So the Pi of A is the odds that A belongs in class I. So how do I figure out what these functions Pi are? Well, I look at the data. I've got this huge data collection of vectors Aj, labels Yj. It turns out I can parameterize this function Pi with a bunch of vectors xi, x1, x2, all the way through xm. And I can express Pi by using this formulation. By plugging the vector A and the coefficient vectors xi into this formulation, that will give me a set of odds. Okay? And by looking at all the data, I'm going to try to figure out what are the correct values of the x1, x2 through xm. And obviously, if I give you a piece of data AI, or AJ, if I give you a piece of data AJ, and it belongs in class I want the AJ transpose XI to be much bigger than the AJ transpose XL for all of the other XLs. Because if this property is true, then Pi of A is going to be very close to 1, and PL of A is going to be very close to 0, right? So by enforcing this property on the coefficients xi, I'll make a correct prediction of all the data in the training set. So you can write down an optimization problem that gives you a set of xi's that has this property, and here it is. It's this maximum a posteriori log likelihood for this, given this collection of data. These are the maximum a posteriori log likelihood vectors xi that maximize this function. And this again is a convex optimization problem, so quite a powerful optimization problem. And a lot of the cycles that are spent in doing machine learning are basically solving this problem. In fact, even when we go to deep neural nets, you've probably all heard the term softmax, okay? The last layer of a deep neural net is often a softmax operation, which essentially is solving this problem, okay, at the very last layer. Now you can do things to modify this problem. You can try to induce sparsity. You can try to make these vectors xi be sparse by adding on some one-norm terms onto this training loss here. And that's useful too in some cases. It's nice to have sparse vectors AI, because then that means you don't have to look at all the features of the agent. Okay, so that's a very important tool. That's multi-class logistic regression. Atomic norm regularization, I probably don't want to say too much about this one, but this comes from a paper in 2010 by my colleagues Ben Recht and Venkat Chandrasekharan and several other people. So they sort of made the observation that in a lot of problems in this area, you've got data that lives in a very high dimensional space, but you can express it in terms of just a few elements in that space, a few fundamental elements. So for example, if you're looking for a sparse vector in a high dimensional space, you can think of that as being a linear combination of just a few vectors of this type, okay, just a few of them. And this sort of structure appears a lot. Like in low-rank matrix problems, you can think of the fundamental so-called atoms to be the matrices of rank 1. And so your job is to find the rank 1 matrices and find out how to combine those rank 1 matrices to approximate your given matrix as well as possible. So they sort of generalize this concept over many different sort of instances in which this low-rank sort of structure appears, and they came up with this theory called atoms, and they figured out how you can write these things down as optimization problems with regularization functions defined in terms of these atoms to sort of, they came up with this general methodology for formulating these problems. That's all I really want to say about this, because I don't have that much more time, and this is a very rich topic as it is. So I'll just refer you to the bibliography. Okay, community detection graphs. This is another one that I don't have time to say very much about. But the problem here, and this is a problem that you can solve using Facebook data and so on, is that you've got a graph. So you've got a bunch of nodes and arcs. The arcs are the lines joining the nodes, and you want to look at this graph and try to figure out what are the communities here. Okay, so we can say that a community is a collection of nodes that are more likely to have mutual connections, mutual arcs between those nodes. They're more likely to have nodes within the community than connections outside the community. Okay? So on Facebook, for example, you'll have a community of friends where you're more likely to connect with each other than you are to connect with people outside the group. So you want to be able to look at this graph and dissect it into different communities, okay, just by looking at the pattern of connections. Now I've drawn the graph here, so it's pretty clear how I can split it into two pieces, right? Oh crap, I can just draw a line down the middle here, right? And you can see that in this group here, there's a pretty dense set of connections. This group is a pretty dense set of connections, but the connections between the two groups is fairly sparse, okay? So you can write this down as a matrix optimization problem. I had a bunch of slides where I describe how to do that, but I've taken it out. It's pretty hard. It's actually a pretty hard problem. You can only prove that it works when there's a big difference between the likelihood of connecting within the group and the likelihood of connecting outside the group. So P is the likelihood that you connect to another node within the group. Q is the likelihood that you connect with outside the group. So you can only really solve this problem if P and Q are quite different from each other. When the two communities are similar sizes and so on, you can solve it. But in general, it's still a pretty hard problem to solve. Hard combinatorial problem. So it's fair to say that there are not really good algorithms for solving this problem in generality. And the problems, of course, are much, much harder. If you've got millions of nodes and very dense connection of arcs, it's very hard to solve in general. Okay, so that's the end of the set of 13. Now let me say a little bit about deep learning. And fortunately, I've got some distinguished colleagues here who are going to say much more and give you a much richer picture of what's going on here. I'll just sort of give you the mathematical basics of what's happening in this problem. So this is my perspective on deep learning, expressed in my notation. that might be very different from what you're going to see now. But this is a typical problem in deep learning. Let me say this. That you're trying to, I can think of it as a multi-class classification problem. Many problems in deep learning are essentially, you give me the vector AJ, you want to try to feed it through the neural net so it will correctly predict that Yj is the outcome, okay, from among, where Yj is one of m different classes. So in this picture here, each of these blue nodes at the output represents a likelihood of AJ belonging to one of 5 classes. So I've got 5 nodes here for 5 classes, okay? And in the end, I want to figure out a set of odds that it belongs to one of these 5 classes. So it's going to do something like a multi-class softmax at the end, or a multi-class logistic regression to give me those odds. So the red nodes here are the input nodes. These are the AJ. So I put in this case, AJ has what, 7 components in it. So each AJ is a vector of length 7. What happens to AJ is that it moves through this neural net. So as I move from layer to layer, the output of one layer gets multiplied by a linear transformation. That gives me the input to the next layer. Within the layer, there's some sort of operation that goes on. Nowadays, it's usually a hinge loss or a ReLU, so-called ReLU operation. Very simple element-wise transformation. And that gives me the output from that layer. And once again, I apply another linear transformation, and the process repeats. Okay? So in the end, as you move through the neural net, this vector AJ gets transformed. As it moves through the neural net, it gets transformed into another vector, AJ. So you can almost think of this as like what happened in kernel learning. In kernel learning, I took the vector AJ, I applied a transformation psi. So in the neural net language, that transformation psi is what happens as the AJ moves through the neural net. And then what happens to the transformed vector is that we do a logistic regression to it, or some sort of classification problem, and we end up with a set of odds that belongs to one of these 5 classes. Now, the tricky part is you've got to figure out what these linear transformations are to apply at each layer. You want to find out what are the most effective set of linear transformations that I can apply inside the neural net so that by the time the AJ has been transformed to another vector, the classification happens very cleanly and precisely, okay? So you've got all this flexibility about how you define these transformations. And the process of learning a neural net is not just the top layer. It's not just figuring out how to transform the AJs and how to convert them into probabilities, but it's the process of how do you do the transformation of the AJ into some vector that's much easier to classify. Okay? So you're trying to learn the WJs and the BJs, which are the elements of or the WLs and the VLs, which are the coefficients of these transformations. So nowadays, as I said, what's happening inside each of these nodes is just a ReLU loss, where you just take the input to the node. If it's negative, you output 0. If it's positive, you just output the number that was the input. So it's just the max operation. What I showed you here is a very, very simple neural net where you've got complete connectivity between the layers. Practical neural nets are much more complicated than this. They have a much more complex structure where there's only partial connectivity, where they're designed in a way that respects the application in some sense that they come from. So there are pooling, there's convolutional layers. Nowadays there's ResNets where there are connections that skip from one layer, they skip over one layer and just directly input it to the 2 layers above, things like that. They're very effective and they've got very interesting motivation. They're LSTM, short-term memory, which are good in situations like speech processing where different elements of the AJ are kind of related to each other. So the features in the AJ actually are sequences of things in time, and so they naturally relate to each other. That can be captured in the neural net as well. So there are many complicated structures that I'm ignoring here that probably other people will tell you about. Okay, so what does the optimization problem look like in the end? So again, you've got to try to figure out what are the optimal set of linear transformations inside the neural net that will do the best job at classifying the training data. So again, I'm trying to match up the AJ with the YJ, but now I've got this X, which is the function that parameterizes the transformation, X here consists of all of the transformations that are happening inside the neural net. So the unknown X, again, I'm trying to find the optimal X that minimizes this loss function that tells me how good a job I'm doing at classifying the data. Okay? And this is a very difficult, non-convex, non-linear, non-smooth optimization problem. Very, very high dimensional problem because X is very large. It has a ton of entries. There's a ton of real numbers in this X. Okay? And so what happens, of course, is people do stochastic gradient. Okay? But there are nowadays many software packages to make this very easy to do. So I've mentioned a few of them here. I'm not up to date on what the cool ones are these days. I know people that I know use PyTorch and TensorFlow. Nowadays they run on GPUs, so you can run them on very fancy architectures. And you know, they've gotten very sophisticated, so you can define the neural net at a very high level, and it will take care of doing all the backprop, the gradient calculation, and so on, that allows you to run to do the training. Okay, so from an optimization viewpoint, this is the training. This is what people do, stochastic gradient. So what's stochastic gradient? Stochastic gradient says that you don't want to evaluate the gradients of this function because it's so difficult and time consuming to do. M is very large. M is typically a very large collection of training data. If you want to figure out the sensitivity of this function with respect to X, you have to look at all the data. Tremendous amount of work, okay? So what stochastic gradient says is don't bother with that. Let's just sample from the data. Let's just take a small subset of M. Let's call it BK, at iteration K. Randomly sample a subset of data. BK might have 100 or 1,000 entries in it, which is only a tiny subset of a data set if it's got millions of data. Let's take the gradients of those with respect to X. Just those entries in the data set. And yes, let's use that as the proxy for the gradient. So GK is supposed to be an unbiased sample of the true gradient. Okay? Now I'm ignoring the fact that you've got non-smoothness in here. So, you know, you just sort of take the gradient anyway. But basically you take a small step in that direction. So machine learning people have their own language. They say this process of evaluating gradients, they call it back propagation, okay, which is like a way to do, you can think of it as kind of like a chain rule or an adjoint calculation, people also call it. The process of figuring out how long of a step to take is very difficult. And there are entire teams of people at the big companies trying to figure out how do you choose the alpha K in the stochastic gradient process. Sometimes it helps to add momentum. I think these packages that I told you about earlier, you're allowed to say, okay, use stochastic gradient, but try this momentum term with coefficient 0.9. Okay, momentum is just where you don't just step in the gradient direction GK, but you add on a multiple of the previous step that you took at the previous iteration. That turns out sometimes to really help the speed of convergence. And so these packages often have options for doing it. Okay. One of the packages, I think Theano, used to call that option Nesterov. It actually had the name Nesterov. You could say Nesterov at option 0.9. And I saw Nesterov himself at a meeting 3 years ago, and I told him that people used his name as an option in the Theano package. And he thought that was brilliant. He didn't know about that. So he thought that was really funny. Okay, so I've got 6 issues and I've only got 10 minutes, so I don't have much time to spend on these. But let me talk briefly about a few issues that are objects of current research. The first one isn't really a current issue, but it's kind of a cultural phenomenon. These people published a paper a few years ago, only 4 or 5 years ago, where they came up with a modification of stochastic gradient called ADAM, and essentially they tried to do a diagonal scaling of the gradient by looking at the different entries of the gradient, aggregating them over many iterations, and trying to find out a good way to weight the different entries of GK to give faster convergence. And they came up, basically it's a heuristic. It's like something people have done in optimization for a long time, where they've tried to come up with estimates of the diagonals of the inverse Hessian. So they come up with a cheap approximation to a second order method. But it's turned out to be quite effective. So effective that this paper has been cited almost 30,000 times. I checked last night and it was like 29,275 citations. So this is like amazing. The convergence theory is not quite subtle. It turned out I think there was an error in the original proof, and people have tried to fix it. But that's kind of beside the point, because heuristically this is like a very popular approach and very effective. Okay, here's another thing that I won't have much time to talk about, but in recent years, and this is what I'm going to talk about tomorrow, many of the interesting problems are non-convex, and therefore they're harder to solve. It's possible that they'll have local minima. You can't be guaranteed that you'll go to the global solution and so on. However, it turns out that many interesting problems in learning, non-convexity isn't really that much of an issue. So it could be that in some problems you can show that the local minima actually are global minima. In other problems you can show that saddle points, these are points where the gradient's 0, but the Hessian has negative eigenvalues. Those saddle points are often strict saddle points, which means you can escape from them easily. Okay, so that happens in a lot of data analysis problems. And another thing is that very often you can get a good initial point. So the problem might be non-convex, but you can solve a problem, an extra problem, that gives you a good initial point, that gives you a starting point that's close to the global solution. So all of these things happen in data science problems, and so global optimization is not that much of an issue. There's a nice review paper, I cited it here, came out last year, where it's a very long paper, but they talk about this whole issue. And they go through a bunch of problems in data science where non-convexity is not that much of an issue. And this is one of them. And it's one of the ones I talked about earlier, matrix sensing, where we've got this unknown matrix X. We're making linear observations of it. We approximate X by, in this case, X is symmetric. So I represent X as an outer product of two skinny matrices Z. Okay? And so I write the problem with, like this, AJ with ZZ transpose. Now this problem is non-convex in Z. Okay? In fact, it's a quartic polynomial, right? But it's not convex. However, they show that under certain assumptions on these observations AJ, that although this problem is non-convex, they can show things like all the local minima are global minima. They can show that you can't get stuck at a saddle point, because if you're at a point where the gradient of f is 0, the Hessian of f will have a strictly negative eigenvalue. And so by looking at the Hessian, you can figure out how to move away from the saddle point and escape the saddle point. Okay? You can also show that for these problems, there's a clever way to initialize to find an initial point so that you will go to one of the global solutions and so on. All right, so that's the second issue. Here's a third issue, which is again a topic of very current research just in the last year and a half or so. People started observing a few years ago that neural nets often have many more parameters than there are entries in the training set. So the number of, if you count up the total number of weights in a neural net, it might exceed by a factor of 10 or 100 or even more the number of items in the data set. Okay? So in fact, it's over-parameterized, and if you run the training long enough, you can actually get a neural net that perfectly classifies the data if you're prepared to run it indefinitely. So people used to say, or used to think in statistics, that this was a bad thing to do. This is overfitting the training data. You're getting a perfect fit for the training data, but if I come along with another piece of data that's drawn from the same distribution as the training data, but it's not actually in the training data set, the conventional wisdom is that this neural net will do badly at classifying that piece of data. But this turns out not to be true. It turns out that these neural nets actually do very well on classifying unseen data. And so people in the community have been trying to figure out, why is this true? Okay, why does this happen? And theories are starting to emerge for this that are really interesting. Another issue in this is that when you run the stochastic gradient on the training problem in the over-parameterized setting, it very often goes to a solution with 0 loss. Why is this? Because this training problem is very non-convex. It's got all these local minima. But somehow it goes to a global optimum. Why is that? So Again, there have been some interesting observations as to why that's true. I'm going to have to skip this because I'm running out of time, but there are a couple of observations that people have made as to sort of explain what's going on. Here is one that I kind of like, that you can kind of show that in an overparameterized neural net, there's actually a whole manifold of solutions. There's a whole collection of different values of the weights that give you zero loss. Okay? So essentially, as you increase the number of parameters, as you increase the width of the layers, the set of solutions grows to fill the space of parameters, right? And so if you just choose a random starting point in that space and run stochastic gradient, the chances are that random starting point is actually very close to a solution with zero loss. And so by running stochastic gradient, it doesn't have to move very far to find a solution. I've got a colleague at Wisconsin, Yingyu Liang, who's worked with a bunch of people on sort of formalizing that observation for multi-layered neural nets and stochastic gradient. They can sort of prove that that's what happens. Here's another thing, and I like showing this picture. It's from a colleague, Misha Belkin at Ohio State. He's got this concept called the double descent curve. And what this is showing is that the x-axis is the complexity of the function phi that I've defined earlier, the function phi that maps the feature vectors to the outcomes. So as you increase the complexity of phi, as you add more parameters to phi, as you increase the depth of the neural net or whatever, you get a richer and richer set of models that you can use to fit the data. Okay? And the y-axis is how good a job you're doing at fitting the data. So the dotted line here is that it's how well you're doing at fitting the training data. So as you, the data in your training collection, as you increase the complexity of the model, you can do a better and better job at fitting the training data, until at some point you can perfectly fit the training data. Okay? And as you increase the model, the complexity beyond that point, the training error is going to stay at zero, because you can perfectly fit the training data. Now what happens to the test data? The test data is the data that you have that's not in the training set, but it's distributed the same way as the training data, right? So this is the so-called classical regime. The conventional wisdom is that as you increase the complexity of the model, you'd also do better at fitting the test data. But once you went beyond a certain level of complexity, you would start to do worse again at fitting the test data, because you'd start to overfit to the training data. So the conventional wisdom was there was some sort of optimal measure of complexity where you did a pretty good job at fitting the training data and also a pretty good job at fitting the test data. So the conventional wisdom was you should stop here. You should settle for a fairly low level of complexity that did a pretty good job of both. But nowadays, in the overparameterized regime, you're out here, right? So you've continued to add parameters far more than you need to interpolate the training data. But what this graph is showing is as long as you do a good job of picking a specific solution in that parameter space, when you're out here, there's actually many different solutions you can find in the interpolation space. But if you're careful about how you pick the solution, if you pick, for example, a solution that has like low norm or something like that, it also does a good job at fitting the test data. And so the test error starts to go down again. Okay? And so in modern overparameterized neural nets, you're sort of out here somewhere, where you perfectly fit the training data, but you also do a good job at the test data. So Misha Belkin has some explanation of this in very, very simplified settings, not in the full-blown neural network setting, but just in the very simplified, like linearly square setting, where he can actually kind of recover this analytically, recover this curve. Okay, and I think I'll have to skip this. Adversarial machine learning, again, I'm up against the clock here, but this is another topic that's been very popular in the last 2 years. People have made the observations that you can fit a neural network to training data, but if you make some very small, carefully selected perturbations to the data, it can misclassify. So in these examples here, these are from the MNIST data set, so it's clear what these digits are, and you can train a neural net to do a great job at fitting the data. But if you just make tiny perturbations to the data, for example, This one here, it's obviously still a 4, okay? But the neural net will misclassify this one. It will tell you that it's something other than a 4. And that's true of all the things in these even number columns. They've got very small perturbations that are carefully chosen to confuse the neural net and force it to misclassify, okay? Whereas, you know, strangely enough, you can make very big perturbations in random directions and the neural net will still behave well. So in this one over here, these are very large perturbations, okay? But the neural net will still tell you that that's a 9. It will still tell you that that's a 6, okay? Even though it's much less obvious. And so the whole area of adversarial machine learning is how do we stop this from happening? How do we make neural nets more resistant to these small, carefully chosen perturbations? This turns out to bring in a lot of new tools from optimization, particularly robust optimization. You can write down the one way to write down the adversarial training problem is to write it as a min-max problem and to sort of classify the training data correctly, not just over the data vectors that you're given, but over an entire ball around those data vectors. Okay, so you can write it as a min-max problem like this. The problem is this is a very difficult problem to solve. It's even harder than the original training problem. Okay, so I've got a postdoc that's working on using robust optimization to solve that. Okay, I'm not going to, I'll skip that part. I guess I'll jump right to this summary. So the summary here is, you know, basically reiterating what I said at the start. Optimization is providing a lot of frameworks, not just for solving the problems, but also for formulating data science, machine learning problems as optimization problems. It gives you a nice way to write down these problems in a concrete way that you can then attack with mathematical algorithmic tools. It's usually not enough to just take an old-fashioned method from optimization and apply it blindly. You have to go and work very hard to customize the features of the algorithm so that it fits the data science application. Because these applications are often very high-dimensional, very difficult problems to solve, and so you have to work hard to come up with an algorithm that really works well. Research in this area has exploded over the last 10 to 15 years. It's still going very strong. There's still many unanswered questions, particularly questions to do with understanding why deep neural nets are working so well in certain applications. And optimization brings a lot to that discussion, I think. And so I think we'll quit there. I've got another slide here, but I think I'll talk about this tomorrow. So thank you very much for your attention. It's time for coffee. Yeah. Preguntas?
Can you make some comment about when some of the features are not numerical but rather categorical? What can you...
Yeah, this is one for the experts. I mean, one way to do that is you just like assign a number to the category and just replace it with a number. But there are probably better ways, but that's above my pay grade, as we say in English. Yeah, I'm not sure what the best way to do that is. RL. Oh, I skipped those slides. But you're interested in that, right? Yeah. So all I know about this is there's discussion going on about sort of a competition between using RL technology and control technology, because some problems can be addressed by either one, right? This process of trying to steer a system to a desirable state and trying to learn a control law, which is like what you call a policy, okay? Policy you can think of as a control law. And so I know there's a discussion going on about policy optimization versus just using traditional control techniques, and what's the sample complexity of these two approaches. There are some situations where it's clearly better to use one than another, but in situations where you can use both, these arguments are being made that you should use one or the other. And the person I talk to most in this space is Ben Recht, who's of course very pro-control, he thinks you should be using this methodology where you don't just try to optimize the policy directly, but you try to identify the transitions that govern how you transition from a particular state and a particular action to the next state. So you should be trying to identify the system first, and then go from there to figuring out what the optimal policy should be. Whereas I know in reinforcement learning, people are tending to try to learn the policy directly, right? That's the most popular approach.
So in URL rule, there's a distinction between drawing between model P,
Yes.
URLs, and model base.
Exactly, yeah, exactly. And people are making arguments. This person, Wen Sun, who interviewed in Madison in the spring, told me that they had an argument that showed that there was an exponential polynomial split in the sample complexity according to these two areas. And I'm sure that's not the final word, because the way you even define these terms, model free and model based, is apparently not clear cut. But we've done. I'm mostly from a control background. I work with control people since the 90s, and we've done some experiments with very simple control networks where it's clearly better to do the identification first and then apply traditional control technology. Ben Recht has done similar things where he's sort of identified the model and then used robust control technology, because of course there's some uncertainty in the model when you do the identification, and he's shown that it's still efficient to do it that way rather than just do it directly using RL. But Sakis, who's he's a very distinguished optimization person who's actually worked in reinforcement learning, Markov decision processes in the past, has become active again in this area. He's just put a book out, and he gave a talk at CDC recently where he sort of discussed pros and cons of this area, of the two approaches. So he has some interesting comments to make as well. So I'd say this is a very active area, and there's a lot of, still very much up in the air as to what the conclusion should be.
I have a question with these problems that have multiple local optima. There are a family of algorithms that allows to find all these local optima. I mean,
there are, but they're they're very slow. If you've got many local optima and you need to find all of them, there are things like multi-stop methods. There's a person that from Mexico actually that used to work on these things back in the 80s, where he would sort of find one local optimum, and then he'd reformulate the problem to find the next one. He used tunneling or something. I actually forget his name. I'm sorry. I have to remember. It starts with G. Yeah, but he used to use this tunneling technique to go from one to the other. But the problem is that often in these problems, there's either a whole space of local optima, they're all connected, or else there's an astronomically larger number of them. So there's no way you can find them all in a practical sense.
Here we have a dynamical system, and we have some parameters that we want to optimize in order to adjust the theoretical dynamical system to the real observed data.
Yeah.
So I think that we have found the global optima parameters that we think that there are similar parameters that behave more or less the same like the global one.
Right.
And for that reason, we are interested in find all these parameters that are different but behave pretty similar.
So you're really interested in exploring the space of local minima, yeah. So, algorithms are just, I think that's a case where you really need to customize the algorithm to your setting. You really need to look hard at the structure of your problem and try to figure out you can't just apply a general global optimization technique. Okay, café. Muchas gracias.